Good morning students. Today is module 3 and lecture 9. So, we are discussing the characterization of various membranes. So, this class will discuss the porous and non-porous membrane characterization and what is the meaning of nominal and absolute rating of membranes. Then we will go and discuss the various characterization techniques for microfiltration membranes, and today's class we will discuss scanning electron microscope, transmission electron microscope and atomic force microscopy AFM. Okay. So, before describing the membrane characterization methods available and the purpose for which they can be employed, it is actually important to understand the pore sizes, what pore sizes we are going to cover. So, we have been discussing about pore sizes, the dimensions, the IUPAC classification since so many days in our various lectures. So, you may understand that as the pore size actually decreases, the membrane characterization also becomes little difficult. So, membrane can be classified based on two categories actually with respect to characterization. So, you can see one is porous and one is non-porous. So, the porous membranes in which the pores are present, and they are basically microfiltration, ultrafiltration, all these membranes, and non-porous membranes are the dense membranes usually used for our RO and as well as your gas separation applications. Now, in microfiltration and ultrafiltration membranes, fixed pores are present, which can be characterized by several techniques. So, the pores are actually fixed, which are already present. So, we need to characterize them. So, they are distinctly visible under different techniques. In order to avoid confusion in defining porous membrane, the term porous has been used throughout this course for both microfiltration and ultrafiltration, instead of frequently using the definition of microporous. So, you can see the definition of porous is more in agreement with the definitions adopted by IUPAC. So, this is the IUPAC classification: macropores greater than 50 nanometer and mesopores in between 2 nanometer to 50 nanometer and micropores lesser than 2 nanometer. The pore size classification given here is referred to pore diameter or pore width. Actually, this also very important to note that you can see let us say this is a pore. Okay. So, what is being we are discussing here about the pore size, actually this is what, this is the pore diameter. Okay, or pore width, but how the pore is actually, so it depends upon the pore shape and its geometry. Okay. So, it can be different types of geometries are available. However, here we are discussing only the pore diameter. So, whenever we are characterizing the pore diameter. So, this implies that microfiltration membranes are porous media containing macropores and ultrafiltration membranes containing mesopores in the top layer. So, hence the definition porous covers both macropores and mesopores and mesopores. So, with the membrane of this type, it is not the membrane material which is characterized, but the pores in the membrane. So, when we are talking about porous membrane characterization, please note that we are characterizing the pores. The membrane material has nothing to do with it. The pore size and the pore size distribution mainly determines which particles or molecules are retained and which will pass through the membrane. So, let us now again discuss a little about the porous and non-porous membrane and how they actually work, their mechanism actually. So, you see the first one a non-porous membrane, which is actually also called as dense membrane. So, they do not have any distinct pores. So, the working mechanism actually is solution diffusion. So, we have heard about solution diffusion in few of our classes and I explained in a nutshell also. Today again I am telling that. So, what is the meaning of solution diffusion is essentially the two factors which play a big role. One is the solubility and the diffusivity of what? Of the solutes that we want to transport across the membrane. So, initially the solutes which are supposed to permeate through the membrane will come and sit on the surface of the membrane, and virtue of their solubility they will solubilize inside the membrane matrix. So, this is okay, this is the membrane matrix. So, once they solubilize, then by virtue of their diffusivity they will travel across the membrane material and then they dissolved out or they permeate out. So, here there are no pores, so solubility and diffusivity is playing an important role. But now let us look into the porous membrane. So, porous membrane, two distinct features can be, transport mechanism can be identified. One is molecular sieving. So, molecular sieving is something in which it is basically size exclusion. So, based on size the permeation is happening. you can see the cylindrical pores which are being shown here, and particles which are larger than the pore size are getting retained on the surface of the membrane, whereas which are smaller than the pore size are permeating through the membrane. So, this is extremely high separation can be achieved with this. So, this is called molecular sieving. And then Knudsen diffusion. So, Knudsen diffusion actually takes place, this is for gas separation. Okay. The separation also achieved very high level of separation can be achieved, and the particles which are smaller than the pore diameter will eventually collide inside the pore, this one length. Okay. So, you can understand, you can call this is the length of the pore. Okay. Right. So, inside it travels. So, it gets collided many times inside the this one, and then travels across its minimum path length, and then comes out in the permeate side. So, this is actually Knudsen diffusion. So, we will learn it in detail when we discuss about gas separation. So, one important but often not clearly defined variable in the characterization of porous membrane is shape of the pore or its geometry. As I told many times during our earlier discussions, then the pore shape or its geometry is of paramount importance, because please do not mistaken that all the pores are cylindrical or parallel in nature. It is never so, except few zeolites that are available, either synthetic zeolites or natural zeolites. We do not have any cylindrical parallel pores existing in any commercial membranes, okay, or any membrane which you prepare. So, in order to relate pore ready to physical equations, several assumptions has to be made. So, there are various equations that actually are being utilized to predict the flux and other parameters to calculate the pore size or pore diameter. Okay. So, two classical equations we are showing is, one is this Hagen-Poiseuille equation, another is Kozny-Kármán equation. So, here this is the Poiseuille equation, Hagen-Poiseuille equation. So, flux equals to delta P dP square epsilon, then 32 x mu p. So, J is the permeate flux here, okay. Delta P is the transmembrane pressure that is applied across, dP is the diameter of the pores which we want to actually find out, epsilon is the surface porosity of the membrane. Understand that it is the surface porosity, okay. So, otherwise you do not confuse with it is the volume porosity, okay. And then x is the pore length and mu p is the viscosity of the permeating fluid. Now, another equation is Kozny-Kármán equation, okay. Here, and the difference between Poiseuille and Kozny-Kármán equation is that in Poiseuille equation the pores are considered to be parallel cylinders, which is actually an assumption. In real life it is not so, okay. But in Kozny-Kármán equation it is assumed that the pores are the voids between the closely packed spheres of equal diameter, okay. I will just try to show you how it will be. So, let us see, this is how. Okay. So, in the Kozny-Kármán it is telling that, okay. So, the pores are the void. So, this is the void, this is the void, okay. This is the space which are the void between the closely packed spheres, okay. But actually in practice it is not so, right. But to simplify the understanding and to use the physical equations to certain extent, so these are actually assumed. So, these methods, models and their corresponding pore geometries are extreme example in most cases, because such pores do not exist in practice. However, in order to interpret the characterization results, it is often essential to make assumptions about the pore geometry. Now, it is not the pore size which is the rate determining factor, but the smallest constriction. So, actually the pore size what we are characterizing is nothing but the diameter of the pore on the surface, right. But that is not actually contributing, or that is not the rate determining factor, and or that is not the thing which is deciding whether a particular solute will be permeating through a particular pore or not. What will decide is the smallest constriction inside the pore, right. So, indeed some characterization techniques determine the dimensions of the pore entrance rather than the pore size. Such techniques often provide better information about permeation related characteristics, okay. So, another factor of interest is the pore size distribution. In a porous ultrafiltration or microfiltration membrane, in general pores in these membranes do not have the same size, but exist as a distribution of sizes. Let us say a commercial membrane, it is written 10 kilodalton is the cutoff. So, what is the inherent meaning of that? Okay. So, it does not mean that all the pores which are actually present in that will allow all the particles which are lesser than 10 kilodalton. It may not be so. So, there since there is a pore size distribution, some pores will be more than a particular size, okay, and some pores will be lesser than a particular pore size. Okay. But whenever we are characterizing membrane or we are talking about pore size, it is the average pore size rather than the pore size of individual pores. So, the membrane can be characterized by either nominal or absolute pore size. Okay. So, with an absolute rating, every particle or molecule of that size or larger is retained. This is your absolute rating. You can understand that anything that is more than this particular size will be retained on the surface of the membrane. So, we can say 100% rejection. Okay. And in the absolute rating should not be confused with the largest particle passed by a filter. Okay. So, it simply determines the size of the largest particle which will pass through the filter under very low pressure differential and non-pulsating conditions. Okay. The absolute indicates that no particle larger than rating can pass through the filter, limiting the type of media to those of consistent pore size where they show 100% retention of particles. On the other hand, a nominal rating indicates that a percentage, usually 95 to 98% of the particles or molecules of that size or larger is retained. So, whenever I am talking about a nominal size, so you understand that here, okay, 95 to 98% of the solutes, okay, will be retained with respect to this particular size. It also represents a nominal efficiency figure or more correctly degree of freedom. So, process conditions such as your operating conditions, concentration of your solutes etc., have a significant role on the retention of the filters, and many filter manufacturers use similar test, but due to lack of uniformity and reproducibility, the use of nominal rating has fallen into disfavor. So, mostly whatever we see nowadays and the ratings, these are all absolute ratings. However, this definition does not characterize the membrane or the pores of the membrane, but rather the size of the particles or molecules that is retained by it. Okay. Since the separation characteristics are determined by larger pores in the membrane. So, another important feature is surface porosity. So, surface porosity is also a very important variable in determining the flux through the membrane in combination with the thickness of the top layer as well as the length of the pores. So, surface porosity means the number of pores actually present in the surface of a membrane, okay, or per membrane area. So, different microfiltration membrane exhibit a wide range of surface porosity, and the ultrafiltration membrane normally show very low surface porosities, almost 0.1 to 1%. Now, when we talk about characterization of porous membrane, it is actually of two types. So, one is structure related parameters, another is permeation related parameters. So, under structure related parameters, so we determine basically pore size distribution, top layer thickness and surface porosity. And in case of permeation related parameters, so we actually determine the separation parameter using some real solutes that are more or less retained by the membrane surface. So, this is called cutoff measurement or cutoff experiments. So, it is often very difficult to relate the structure related parameters directly to the permeation related parameters, because the pore size and shape are not very well defined. Even though we are seeing the pores or pores diameter or the surface from the top surface, but we do not exactly know what is the shape and geometry of the pores inside the membrane matrix. So, that is actually going to play a big role in the separation. So, let us now understand the different types of pores actually. Okay. So, the configuration of the pores, either cylindrical, packed spheres used in simple model description, deviate some times drastically from the actual morphology actually. So, those are idealistic situations because they are assumed. In real life it is not so. So, a combination of a well defined characterization techniques can give information about membrane morphology, which can be used as a first estimate in determining possible fields of application. So, you can see this your model or this one ideal pores looks like this, okay, cylindrical parallel pores. However, your actual pores are like this. So, this was I was talking about the smallest constriction. You can see this is the pore diameter that actually you are going to characterize for this particular pore. Okay. But you see how the flow will takes place from here. Okay. If the size of the solute is smaller than this pore diameter, the solute will flow. okay, inside the pore. However, then it will come and then it will get retained on this particular constriction, because there is a smallest constriction, the solute is not able to permeate through that constriction. So, after some time what will happen, that this particular pore, okay, will be of no use. So, this becomes just like a dead end pore, and it is not contributing to the permeation. So, this is a dead end pore in which the pore is actually sealed at the bottom. That means, anything that is coming, okay, are getting deposited inside this particular dead end pore, and this is not contributing to your separation. And microfiltration membranes possess pores in 0.1 to 10 micron range and are readily characterized with various techniques. So, let us start discussing techniques. Today we will discuss three: SEM, TEM and AFM. So, under electron microscopy we have two distinct techniques. One is scaling electron microscopy, another is transmitter electron microscopy, SEM and TEM. So, SEM is a very convenient and simple method for characterizing and investigating the porous structure of microfiltration membranes. So, the resolution limit of a simple electron lies in the range of 0.01 micron, that is 10 nanometer range, whereas the pore diameters of microfiltration membranes are in 0.1 to 10 micron range. Now, let us start understanding how the SEM works and what is the different parts. So, students, in this particular lecture and even our consequent lectures also, when we are discussing characterization, I will be giving the techniques little more in detail. So, because it is very understood, once somebody is working with a membrane, so he or she must understood the analytical techniques, their principles, how a particular instrument works, because it will immensely help you to understand what is actually happening inside the instrument when we are going to characterize it, and it will enhance your knowledge. Okay. So, let us understand how this TEM works. So, interaction of electron beam with specimen. So, we have unscattered electron. So, incident electrons which are transmitted through thin specimen without any interactions with specimen. So, these are called unscattered electron. Transmission of unscattered electrons is inversely proportional to specimen thickness. Thicker area have fewer transmitted unscattered electrons and they appear darker. Okay. So, a area if it is thick, okay, let us assume the membrane only. Okay. If it is very thick, then what will happen, that we have very few transmitted unscattered electrons. So, due to that particular region will appear dark in your final micrograph or image. So, thinner area have more transmitted electrons and they will appear brighter. So, we can read actually more easily what is inside. Okay. So, by this constant image is actually created. So, your contrast image is actually getting decided by how much unscattered electrons are transmitted. Okay. Then elastic scattered electron. So, incident electrons that are scattered by atoms in specimen in elastic fashion. So, that means there is no loss of energy. Okay. And scattered electrons form diffraction pattern that yield information about orientation, atomic arrangements and phases present. Then another form is inelastic scattered electron. So, incident electrons that interact with specimen atoms in inelastic fashion, losing energy during interaction. So, the difference between elastic and inelastic is that in elastic there is no loss of energy, whereas in inelastic there is a subsequent amount of energy that is getting lost during the interaction. So, loss of energy is the characteristics of interacting elements of a sample. So, energies are unique to properties of each element and can be used to determine composition and oxidation states. Let us understand how a TEM works actually, what is the different parts. So, you can see the figure on your right hand side. So, this is the structure of transmission electron microscope and its optical path. You can see there is something written high vacuum, because the TEM itself, the entire setup works under vacuum. So, we will subsequently learn why it is. Okay. So, TEM similar to a transmission light microscope has the following components. So, there is a light source, there is a condenser lens, there are specimen stage, there are objective lens, there are projector lens, then there is screen and photography film and CCD camera. So, you can see there is a electron gun here. Okay. Then this one. Okay. Then we have accelerator, then we have first condenser lens, second condenser lens. Okay. Then we have a specimen. So, this is the specimen. Okay. your membrane material or anything, any polymer, and then it passes through the objective lens, and then there are intermediate lens, then there are projector lens, which is finally projecting the image to the screen, and the intermediate lens and projector lens actually helping in magnifying the rays or image whatever it is getting produced due to the secondary scattered electrons through the specimen. So, in the basic difference between SEM and TEM, we will discuss SEM later on. So, is that in TEM the electrons are passing through the membrane, whereas in SEM it is just scanning across the top of the surface. So, the main difference are that in a TEM the visible light ray is replaced by a electron ray, and glass lenses for visible light are replaced by electromagnetic lens. The TEM contains further features arising from using electrons as illumination. For example, a vacuum environment is required, as I was telling, the vacuum environment is required for TEM, which is not so for SEM or AFM. So, because collisions between high energy electrons and air molecules significantly absorb electron energy. So, if there is no vacuum, when the electrons very highly excited state, they will collide with each other and along with the air molecules, and they will try to absorb the energy. So, that is not good. So, that lot of energy will be lost, and eventually you will not get any particular image which we are actually supposed to. So, different characteristics comparison of TEM with a light microscope are provided. So, let us look at this particular actually table. Here it is telling us what is the difference between a transmission light microscope and a transmission electron microscope. So, the specimen that is required for both for TLM is that a polished surface and a thin section less than 100 micron is fine. But for TEM it should be very thin, less than 200 nanometer. So, best resolution is 200 nanometer, and for TEM it is 0.2 nanometer. So, similarly magnification range is very high in case of TEM. Sources of illumination is high speed electrons. That is why TEM is a very sophisticated instrument, and we are using vacuum to do the imaging. Lens are electromagnetic, whereas at TLM only glass lens are used, and operation environment is either air or liquid, or here it is high vacuum in TEM. And we can see the image formation by naked eye, just by looking at the inside the lens, whereas in TEM it is on phosphorescent plate, that image is that is getting formed. So, this is a structure of the TEM actually. You can see the electron source is here, then the beam is coming here. So, here it is, here the specimen is being held here. So, that means the membrane or polymeric material whatever it is, then whatever the electrons that is transmitted through the through the specimen are coming to this electromagnetic lens. Then it is magnifying and it is projecting to this another lens here. Then whatever it is coming out to this particular lens can be viewed in a screen. So, a source at top of microscope emits electrons that travel through the vacuum in column of microscope. There are multiple lens, and depending upon arrangement of a particular TEM, we can have various types of lens. So, vacuum is essential to prevent strong scattering of electrons. So, electromagnetic lenses focus electrons into a very thin beam. So, this is very important in case of TEM. Electron beam travels through specimen and then through electromagnetic lenses. So, at bottom of microscope, unscattered electrons hit fluorescent screen, which gives rise to image of specimen with its different parts displayed in varied darkness according to their density. So, let us understand the different electron sources. So, high energy electron beam used for illumination is generated by electron gun. Electrons are emitted from the surface of cathode and accelerated toward anode by high voltage to form a high energy electron beam with a energy E equals to small e V naught. So, V naught is the voltage, and additional electrodes are placed between cathode and anode to stabilize electron beam. So, this is how actually the electron gun looks like. There is a cathode and there is a anode through which actually the electron beam is getting generated. So, wavelength of electrons is determined by the electron energy. Since resolution of microscope depends on wavelength, hence for TEM acceleration voltage determines the resolution to large extent. So, it is the acceleration voltage which is actually determining the resolution. So, TEM resolution is calculated for alpha equals to 6.5 into 10 power of minus 3 radians. Okay. So, you can use this particular equation. So, 200 kilovolt is commonly used and meets most resolution requirements. So, you can see in this particular table it tells us the acceleration voltages, the electron wavelength and the TEM resolution, corresponding TEM resolution. So, two basic types of electron guns are used, thermo-ionic emission gun and field emission gun. So, thermo-ionic emission we can use either a tungsten or lanthanum hexaboride filament so that is the cathode. The cathode is the source of actually generation of the electrons. Okay. During operation filament is heated by electric current to a very high temperature. High temperature provides the kinetic energy for electrons to overcome surface energy barrier and enable conduction of electrons in filament to leave the surface, then they will move ahead. So, intensity of electron beam is determined by filament temperature and acceleration voltage. So, this is the characteristic features of lanthanum hexaboride gun, which is most widely used actually. So, it has a better cathode, then more widely used, lower cathode temperature is required. So, we do not need very high temperature actually to generate the electrons, generate higher intensity electron beam compared to other gun type, longer life than a tungsten filament. Tungsten filament needs frequent replacement actually and high level of vacuum is required. Okay. So, this is actually a little disadvantage that in case of lanthanum hexaboride gun a high vacuum level is actually required. Then let us understand what is a field emission gun. So, very high electric field is applied to metal surface for electrons to overcome surface potential barrier. So, the difference between field emission gun and your thermo-ionic gun is that in case of field emission gun you need to supply more energy or you need to supply more temperature to the cathode, so that it will overcome the surface potential barrier. Okay, so that the electrons will get released. However, that is not true in case of the thermo-ionic guns. Okay. So, during operation electrons are physically drawn up from a very sharp tip of a tungsten crystal. Okay. So, you can see this is the tip actually of a tungsten crystal, this is the support of the tip. Okay. And almost 100 nanometer the tip radius is under an applied voltage feed. And field emission gun generates the highest intensity electron beam. It is 10 to the power 4 times greater than that of the tungsten filament gun and 10 to the power 2 times greater than that of the LaB6 gun. So, two kinds of field emission guns are there, thermal and cold gun. So, thermal field emission gun works at elevated temperature of around 1600 to 1800 Kelvin, but lower than that of thermo-ionic emission gun, and cold field emission gun works at room temperature. So, that is the beauty of cold field emission gun. So, you can see this the table actually is giving us an understanding about the two types of guns. Total comparison, it is tungsten is there, LaB6 is there, then under field thermal and cold. You can see that the operating temperature is the lowest for the cold one. Okay. And the brightness comparison is also given, requirement to vacuum comparison is also given. Okay. So, SR is the steradian, that is the unit of the solid angle. So, then let us come to the electromagnetic lenses. So, what are those? So, all lenses in electron microscope are electromagnetic. So, charged electrons interact with magnetic fields and magnetic force deflect or focus an electron beam. So, if an electron is moving with a velocity v, experiences a magnetic field of strength B, then it experiences a force equals to BeV. Okay. Right, in direction that is perpendicular to both the direction of motion and magnetic field. Now, in typical electromagnetic lens, magnetic force field cause the electron to travel in a helix along the lens. This helical path finally converges to a point similar to light optics. A coil consisting of a large number of turns of wire is wound on a soft iron core, which has very small accurately machined air gap across the field, across which the field is actually produced. So, by varying the current passing through the coil, magnetic field strength and hence focal length of the lenses can be varied. Okay. Actually, you are controlling the current which is passing through the coil. So, by doing that the magnetic field strength and the focal length of the lenses can be varied. Okay. So, this is an arrangement of the electromagnetic lens. Then condenser lens. Now, 2 or more condenser lens are present in actually TEM. So, condenser lens system controls beam diameter and convergence angles of the beam incident on a particular specimen. Okay. And the first condenser lens controls the demagnification. There are 2 condenser lens actually, 2 or more, usually 2. 2 is minimum basically. So, the second lens control the convergence of angle of beam incident on the sample. Okay. So, this is a condenser lens optical path which is shown in this particular image. Here you can see the first condenser lens. Okay. This is the first condenser lens. Okay. So, this is what it is doing, it is doing the demagnification of the incident ray which is passing through it, and then the second one is actually converging the angle of incidence. Okay. And then it is falling on the surface of the beam. Okay. So, here it is converging, you can see like this, and this is the sample or the specimen on which it is falling. Then let us understand the specimen. A TEM specimen should be thin as possible, okay, because here the electrons are getting transmitted through the specimen. So, if it is thick, then transmission will be very less, and thin specimen cut into usually 3 mm disc is mounted in a specimen holder to insert into the TEM column. So, this is a specimen holder, this image, okay, and this is the magnification, here you can see. Okay. So, you can take it like this, it is a slip type of system arrangement in which you are going to space your grid. So, there is something called a TEM grid. So, we call it actually TEM grid. Okay. Smaller specimens are mounted on a 3 mm disc, it is called grid, okay, usually made up of copper. So, to prevent specimens from falling into the TEM vacuum column, because it is under vacuum, no, the specimen should not follow. So, you have to be very careful. So, here this one care should be taken in such a way. So, you are seeing now, please see this, these are specimens. Okay. So, it should be in such a way that it is the size is more than this particular size of the grids here. This is one grid, okay, this particular grid. So, the specimen size should be more than the grid size, a single grid size. Also, otherwise the vacuum will try to pull it inside the TEM, right. So, grids are made up of various materials. So, copper is usually used. We can have nickel, gold plated copper and gold plated nickel also. So, those are very costly, so that is why usually copper grids are used. So, a phosphor screen is used to convert the electron image to visible form in case of TEM. The screen consists of a metal plate coated with a thin layer of powder that fluorescents under electron bombardment. Okay. Traditionally, zinc sulphide with small amount of metallic impurity is used. After phosphor screen converts electron image to variation in visible light intensity, it is recorded. So, presently charged coupled device CCD, which is very famously known as charged coupled device. Cameras are used for digital image recording. Simplest digital camera use a computer based video system directed at a phosphor screen. So, resolution is something that is of very importance for TEM, because it is this feature which is actually distinguishes itself from other scanning, other electron microscopy techniques. So, assuming mu equals to 1 and negligible change of refractive index, resolution of electron microscope can be written as R1 equals to 0.61 lambda divided by mu sin alpha. So, here lambda is 0.0037, that is the wavelength of 100 kilovolt electrons, and alpha equals to 0.1 radians, usual to more or less approximately to 5 degrees. So, your resolution that you will get will be 0.02 nanometer, but this limit is difficult to achieve due to aberration, right. So, this is the TEM image of a porous membrane. So, you can see there are 4 distinct images, micrographs we call it, TEM micrographs. So, it is a NPN membrane. So, NPN actually nanoporous silicon nitride, NPN stands for, manufactured with different nanomorphologies. So, the sizes and shapes can be ranged from largely open to pitted and underaged. So, A and D you can see that this one, okay, this and this. So, they are largely open structure, okay, and B and C, right. So, this one and this one, okay. So, they are pitted or underaged. So, this is you can see there are some white arrows, okay. These are the white arrows. So, that indicate open nanopores in low porosity films. You can see very small open nanopore here. Here also you can see this one, okay. So, they are indicative of the small open nanopores in low porosity films. Now, students, let us understand how the SEM works and what is its principle of operation and what is its different parts. So, scanning electron microscope is widely used type of electron microscope. It examines microscopic structure by scanning the surface of the materials. Now, please again I am repeating that the difference between SEM and TEM is that in TEM the electrons are getting transmitted across the surface of the polymer or membrane, whereas or any sample, whereas in SEM the electrons are not getting transmitted, rather they are scanning the surface of the material. So, it is the surface that is getting characterized. So, similar to scanning confocal microscope, but with much higher resolution and much greater depth of field. The SEM. The most important feature of the SEM is a 3-dimensional appearance of its image, because the depth of the field is high. So, for example, the depth of the field can reach the order of tens of micrometers or 10 power of 3 magnification, or the order of micrometers or 10 power of 4 magnification. As SEM is a relatively easily operated and maintained in comparison to a TEM. Please look at this particular image, which is showing the structure of a SEM. So, there are several electromagnetic lenses, including condenser lenses and one objective lenses. So, here also minimum 2 condenser lenses are used. Please understand that whatever we have discussed under TEM, so most of them also holds good for SEM also, like the number of condenser lens should be minimum 2, okay. It can be more also, but minimum 2. Okay. So, and then electromagnetic lenses are used for electron probe formation, not for image formation, as in the case of TEM. So, this is another distinctive feature. So, in TEM the electromagnetic lenses are doing the image formation, whereas in SEM they are not doing any image formation, they are helping in electron probe formation. So, here the 2 condenser lenses are used. So, they reduce the diameter of electron beam. Okay, they are condensing, that is why the name condenser lens. So, objective lens further demagnify the cross section of electron beam and focuses electron beam as probe on a specimen surface. Okay, you can see this is your specimen, this is actually hold in a tilted position. So, objective lens functions like a condenser. So, we have a first condenser lens here, we have a second condenser lens, this is the electron gun which is providing your electrons. Okay. Then there are different types of apertures are there. Okay. There are different scan coils are there, which is used for magnification purposes. Okay. Then we have final lens aperture, through which final electrons with high energy are passing and getting and bombarding on the surface of the specimen, and then whatever the secondary electrons are coming out of this specimen, they are being detected by the help of a detector. Okay. And then there is amplifier, which is helping in amplifying the images, and then we see whatever the image in a display screen. This is in contrast to TEM, where objective lens does the magnification. So, electron probe is scanned across the specimen and the procedure then is raster scanning. Okay. So, raster scanning causes the beam to sequentially cover a rectangular area on specimen. Signal electrons emitted from specimen are collected by detector, amplified and used to reconstruct the image according to 1:1 correlation between scanning points on specimen and picture points on skin of cathode ray tube. So, CRT. Let us understand what is that actually, how CRT looks like, the cathode ray tube. So, cathode is raised to high temperature by heating electrically when electrons escapes from the surface. So, they must over the resistances, okay. And then after that only, so sufficient amount of minimum temperature amount of energy to be supplied, so that it will cross the barrier, okay. And so that electrons will come out from the cathode. So, accelerating anode with small aperture at center is maintained at high positive potential relative to the cathode to form a narrow beam and travel to screen. So, you see this is the cathode actually, okay, and this is the filament, right. So, then we have a accelerating anode here, right. So, there is a small aperture inside the accelerating anode, okay. So, then there is a focusing anode here, this one, okay. Then there are plates for horizontal deflection, and then there are plates for vertical deflection. So, there is a area spot where the beam of electrons strike fluorescent screen glows very brightly. Control grid regulates number of electrons reaching anode and hence brightness of spot on the screen. So, this horizontal plates and vertical deflection plates, they are helping to actually neutralize the different types of electrons that are passing out of the anode. So, focusing anode ensures that scattered electrons in slightly different directions are focused back to a narrow beam and arrive at same spot on screen. Beam of electrons may be deflected using electric fields between deflecting plates horizontally or vertically if required. So, it is actually what is the requirement, depending upon you can use either one of these or both also. So, vacuum is maintained in tube to avoid collisions of electron with air molecules. So, CRT converts your electronic signals to visual display. Okay, cathode ray tube. So, electrons strikes a phosphorus screen. The screen here actually is phosphorus screen, okay, and causes a bright spot to appear at the point of impact. So, there is a when they are impacting, it will create a bright spot. Now, this spot actually moves rapidly. The spot move across the CRT screen to form a series of tightly packed lines. This is how it looks like. So, since spots swept very quickly along the screen, phosphorus screen, so a continuous image is visible. So, they are very fast. Okay. So, the spot on CRT mimics the movement of electron beam on specimen. Now, let us understand the different types of detectors. So, detectors plays a very important role in electron microscope, because ultimately this is the instrument which is detecting whatever the incident ray is coming out from the microscope and then converting it into the final image. So, ET detector, which is called Everhart-Thorney detector, is commonly used in SEM. So, it mainly detects the secondary electrons. So, ET detector consists of a scintillator photomultiplier system. So, a photomultiplier is a unit which actually amplified the this one electrons, okay, and secondary electrons strike the scintillator, that is a phosphor, which then emits photon. Okay. So, this is a scintillator, you can see. Okay, this is photomultiplier. So, there are grids here, you can see there are grids here 0 to 200 volt. Okay. Then once the secondary electrons strike the scintillator, okay, then it will emit the photons. So, this photon is transmitted through light pipe into a PMT, which converts the photon into pulses of electron, which is amplified and used to modulate the intensity of the CRT. You can see this is the specimen, okay, how incident beam is falling here. Okay. Then secondary electrons are getting generated. Yeah, these are secondary electrons, these are back electrons. Okay. So, the energy of secondary electron is low to excite scintillator, and so they are first accelerated by applying bias voltage of plus 10 kilo EV. A grid in front of detector is either positively or negatively charged depending upon the signal detection. When given a positive charge, detector attracts signal patterns electrons, particularly secondary electrons. Now, grid improve collection efficiency by collecting even those secondary electrons which were initially not moving towards the detector. So, when given a negative charge, it screen out secondary electrons with low energy and then detect, and only backscattered electrons, which are known as BSCs, travelling directly towards the detectors. Okay. So, BSCs are typically deflected from specimen at large angles with little energy loss. So, ET detectors has lower efficiency for backscattered electrons due to low solid angle of collection, and there are specialized detectors for BSCs. You can see this particular structure actually. It is again showing how the light actually the backscattered electrons are going back to the scintillator. Okay. And here also you can see what is the, this is the specimen surface. Okay. This is the specimen surface. So, electron are getting bombarded on the surface of the specimen, then secondary electrons are coming here. Okay. You can see that this is the area which the backscattered electrons is actually occupying. So, if the backscattered electrons will be more, it is not good for the imaging purposes. Okay. So, you need to minimize that. The SEM image is not magnified by any lens as opposed to TEM, okay, where magnification is determined by the objective lens. So, magnification of SEM is determined by the ratio of linear size of display screen to the linear size of the specimen that is being scanned. Since it is a scanning process actually, so that is why the magnification is defined or determined in a different way rather than that of a TEM. So, SEM is able to provide image magnification from about 10x to greater than 1 lakh x. Okay. Raster display on CRT is larger than corresponding to raster scanned by electron beam. So, you can see, so this is the raster that is getting displayed on the CRT. So, this is actually larger than that of the raster on specimen. Okay. So, your linear magnification, it is nothing but the side length of the CRT divided by the side length of the L. So, this L divided by this L. So, as for example, if electron beam is made to scan a raster of 10 micron to 10 micron on specimen, an image is displayed on a CRT of 100 mm to 100 mm, then the linear magnification will be 10,000 x. So, SEM resolution, so pixels. So, image performance in SEM can be explained on the basis of picture element or pixel. So, please see this particular figure. The amplified signal from detector make a minimum spot size of 100 micron in CRT, and 100 mm square CRT such as used in photographic image recording can therefore contain 1000 discrete picture element or pixels of size 0.1 mm. Okay. So, the electron beam scans a raster side of side L. So, this is the raster scanning of the specimen, and this is the length is scanning of that is getting reflected on the surface of the CRT. Okay. And the rasters also can be thought of as arrows of pictures point or pixels. You can see that these are pixels, okay, right. So, spot on CRT mimics movement of electron beam on specimen. For each of the pixels on CRT, there is a corresponding pixel on specimen. So, size of specimen pixel is given by p equals to 100 by m micron, okay, where m is actually magnification. So, resolution is defined as smallest separation of 2 points that microscope can detect as separate entities. So, here you can look at. Okay. So, these are the 2 pixels that contains being marked as and B. So, these 2 pixels should be distinctly visible separately. That is how much they are distinctly visible is actually the resolution. So, in order to resolve 2 features A and B in figure, they must occupy separate pixels. So, if they occupy, let us see the same pixel here, both A and B, okay, are occupied in the same pixel, then the problem will be that the resolution will be very low. We cannot see A and B completely and differently. So, that is why they should occupy different pixels. So, therefore, working resolution of SEM cannot be can be no better than specimen pixel size p as given by the above equation. So, in a quick nutshell, let us understand the principle of SEM again. So, a narrow beam of electron with kinetic energy in the order of 1 to 25 kilovolt hits the membrane sample. Okay. So, there are primary this is a filament source, okay. Then there the which is actually generating the primary electrons, then it passes through the condenser aperture 1 or 2, we have 2 condenser lens, okay. Then it goes through another condenser aperture and finally bombarding the sample. Okay. Then what it is doing? It is generating secondary electrons as well as some BSEs. Okay. Now, these secondary electrons are getting detected by the detector. So, the incident electrons which are called primary electrons, they are having high energy electrons, are reflected are called secondary, and those are reflected are called secondary electrons. Now, these secondary electrons having low energy are not reflected, but liberated from the atoms in the surfaces. This we need to understand that the secondary electrons are not reflected. So, they are liberated, okay, from atoms in the surface. So, they mainly determine the imaging what is seen on the screen on the micrograph or on the micrograph. When membrane is placed in the electron beam, the sample can be burned or damaged depending on the type of polymer or accelerating voltage employed. This can be avoided by coating the sample with a conducting layer, often a thin gold layer, to prevent charging of the surface. The preparation technique is very important, but many times it is overlooked. Okay. Because what will happen that if the preparation is not good, then you will get a bad image. Other important problems associated with drying of a wet sample, because the capillary process involves damage of the structure. So, you cannot go for a sample which is wet. So, you can use either cryo unit or you can use a liquid with a lower surface tension. So, usually water is used because water's surface tension is one of the lowest. Okay. And then the choice of the liquid also depends on the membrane structure, because since all the liquids must be non-solvent for the membrane. Otherwise, if you are going to use a solvent which is organic in nature, maybe alcohol or something like that, then it may happen that it will swell the pores of the membranes, or it will swell the membrane, their pore size will eventually increase, which you may not understood, but it will eventually happen. So, example of typical sequence of liquid actually is water. The water is always prepared, followed by ethanol, butanol, pentane or hexane. Okay. So, the last solvent is alkane, which has a very low surface tension and can be easily removed. In polymers with a high to very high water absorption, problems can arise because the structure may be damaged or altered during drying if they contain liquid. So, for this type of samples, usually low temperature scanning electron microscope, which is also known as LT-SEM, may be used. There is a cryo unit fitted to that this microscope. Wet samples are quenched in liquid nitrogen and brought into the cryo unit, where the frozen water is partially sublimed. The frozen water takes care of conduction, but it is also possible to coat the sample with gold layer by a deposition technique. But that you know, coating by gold layer, it is time consuming as well as it is costly process. So, however, it is done if you are your specimen, if you want to a particular image without any hindrance, no artifacts, nothing, then it is better to coat with a gold layer. So, without this deposition technique, the magnification attainment is not very high, and also that freezing can damage the structure also. However, this is very useful technique for highly swollen sample. The samples which are actually highly swollen, highly porous, and if you are using a liquid inside that and that gets freeze, then it is fine in a cryo unit. But those who are not swollen and not very microporous, for them actually if you coat it with gold, then it is better. So, this is the scanning electron microscope of a particular membrane. Same is the technique which will actually give us the view of the top surface as well as the cross section and as well as the bottom surface. So, any asymmetric structure also can be identified if you look at the cross section. Okay. Figure shows the top surface of, this is the top surface of a porous polyethermide ether imide membrane. So, micrograph of this kind allow pore size distribution and surface porosity to be obtained. Also the pore geometry can be visualized. See, you can see this is the cross section. Okay. This is the cross section of a PS 300 membrane. You can see little the structure of the pores. You can see this particular pore more or less it is a cylindrical pore. Okay. However, the constriction here in this particular area is little lesser and then it become wide. Okay. So, it is very easily, if you use this cross section, then you can easily identify your asymmetric structure. We can see. Okay. So, this is a dense layer or any layer. So, we can then see the porous layer here. Okay. So, easily if you look at the cross section, it will tell us easily whether the membrane is asymmetric membrane or not. So, there is something called FESEM or it is called field emission SEM. So, FESEM produce a cleaner image, less electrostatic distortion and spatial resolution, then almost 3 to 6 times better than that of a SEM. So, it is a high vacuum system. So, low final spot diameter makes FESEM the high resolution instrument. So, FESEM achieves a small probe diameter and high probe current. Let us understand quickly that FESEM is a technique in which the field emission is being used and its resolution is 3 to 6 times higher than the resolution of the usual SEM. So, you can understand and see this image which will be very clear. So, you can see this is a SEM image of a carbon particles. Here you can see that particles are also clearly visible. However, if we use the FESEM same material, it will give a distinct features, more clear, more high resolution and brighter image. Okay. So, now students, let us understand quickly what is AFM. Okay. At AFM is atomic force microscopy. It was invented almost back in 1986. If I correctly remember, scientists at IBM have actually discovered this AFM technique. So, AFM has proven to be a useful addition to the microscopy family, it providing imaging and force measurement. Okay. That can interrogate the nanoscale properties. So, basically useful to study the nano properties. AFM has been used with great success to provide novel insight into the film type of structure. AFM can image on non-conducting surfaces with nanometer scale resolution in air and even under liquids. So, soft organic surfaces can be successfully imaged with AFM due to the presence of microfabricated cantilevers. Let us see, actually we will see in an image how it actually works. So, AFM is rather new method to characterize the surface of a membrane. There is a sharp tip with a diameter of almost 100 angstrom, very small, very thin, which is scanning across the surface. Okay. So, here in the SEM, the electrons are scanning on the surface of the sample, but here in AFM there is a tip. Okay. The cantilever is holding a tip, that tip is actually scanning like this. okay, with a constant form. So, here London van der Waals interaction will occur between the atoms in the tip as well as surface of the sample, and those forces are detected. They will eventually result in the micrographs. So, this will result in a line scanner profile. The use of microfabricator cantilever allows to operate at a very low forces, less than 1 nanonewton. This makes it possible to apply this technique to soft surfaces, okay, as in polymeric membranes. In general, this technique is applied at constant force between tip and surface, and this gives then an image of the surface in certain direction. So, let us look at the AFM images. You can see in this side, this is the schematic drawing of a surface scan of a ultrafiltration membrane. Here this particular image, there are 3 images. It is showing the AFM images of a ultrafiltration substrate membrane, this one A1, okay. Then this is the B is the top layer of the unmodified membrane, and C is the top layer of the serenol grafted membrane, okay. So, what we if we actually make it little bigger size, then we can understand it little better. However, we can understand from the image that there is distinct features which can be noticed for different types of materials. So, this is the AFM instrument actually works. So, there is a laser diode, and this is the cantilever which is holding this is your sample. This is the tip which I was talking about, okay. Okay. So, the tip actually is doing the scanning, that is scanning the surface of the sample, okay. Then whatever the amount of forces, what is the sorry not amount, what are the types of forces that is actually getting generated by virtue of this scanning, okay. They are getting detected using a PSPD detector. There can be different types of detectors, and finally, this detector is amplifying and doing so many other processings, okay, intermittently, and then getting resulted into an image which will look something like this. So, the surface of the membrane can be scanned in air without any pretreatment. This is another advantage of the AFM. So, the obtained line scans do not really reveal the possible position and size of the pore, also an indication of surface roughness and surface corrugation. So, AFM is the only one technique which will give us the indication of a surface roughness. Okay. Due to this surface roughness, it is often difficult to obtain a pore size distribution. So, PSD or pore size distribution is bit difficult to get in case of AFM, which is very easy to do it in case of here SEM. So, however, in combination with electron microscopy and other technique, it might be useful technique. So, also information on surface roughness might be useful when support layer are characterized for composite membranes. When imaging a soft sample, the tapping mode and intermittent contact mode is used. The intermittent contact of this imaging mode reduces the degree of friction or drag. To achieve the intermittent contact, a vibrating cantilever is used actually, okay. So, technique, so that cantilever is actually vibrating, and change in their vibrational parameters are monitored as the cantilever scans the surface. So, in response to change in topography, the piezo scanner moves up and down to maintain a constant vibration of the cantilever, and the feedback signal is used to produce the image. So, an advantage of this imaging mode is that measurement of the phase angle between the free oscillation at the end of the cantilever and the imposed driving vibration provides a map of phase angle across the surface. So, actually this is referred to as phase imaging. This is captured simultaneously as the standard topographical data. AFM can measure the force of interaction between surfaces. So, AFM has the advantage of allowing the imaging and identification of points of interest on a surface prior to measurement of the forces of interaction. So, it also allows the direct measurement of forces as opposed to techniques that estimate force from the application of a shear to a position, such as to a cell population. In addition, surface forces are measured over very small contact areas. So, that actually minimizes the contamination problem. So, students, please have a look in this interesting figure, okay, images. So, in a single this one figure, you can see there are 6 distinct images. So, 3 each. So, the first 3 here A, B and sorry, A, C and E. So, these are corresponding to the AFM. The first one is this is AFM. Okay, this is scanning electron microscope, and this is STEM. So, AFM, TEM and SEM and TEM images of a TFC. So, a thin film composite membrane. Similarly, here this is the AFM, this is the SEM, and this is the TEM image of a TFN. So, thin film nano composite membrane. Okay. So, you can see how the images are distinct actually in case for a particular substrate, in case of a AFM, in case of a SEM and in case of a TEM. So, let us wind up in today's class. So, in summary we will just try to tell you that SEM is a very simple and useful technique for characterizing microfiltration membranes. So, a clear and concise picture of the membrane can be obtained in terms of top layer, cross section and bottom layer. In addition, we can find out porosity and pore size distribution, right. So, care must be taken for the preparation of the sample. So, whereas AFM is a method to determine the structure of a surface, the pore size and porosity can be obtained from the cross section of the AFM images, but usually we do not prefer to do so. We can do it, however, we used to do it from our SEM. If you have SEM, if you do not have the SEM, then AFM itself, from AFM micrographs also we can find out. So, the advantages of this technique is that no pre-treatment is required. This is one of the beauty of this particular technique, and it can be the measurements can be carried out in under atmospheric conditions or ambience. So, a disadvantage is that high surface roughness may sometimes result in images which are difficult to interpret, because the tip is getting is doing the scanning. No, so there is forces which are high getting generated, and they may damage the surface actually. So, high forces will may damage the membrane material, but not all. For few polymeric material are susceptible to such damage actually. So, students, today we understand the microporous so this one membrane characterization techniques, 3 important characterization techniques, SEM, TEM and AFM, and next class you can refer these books, okay. And in next class we will understand some other beautiful techniques, which is called bubble point method, bubble point with gas permeation method, mercury intrusion method and permeability method. So, some of these methods like your bubble point method as well as permeability methods, so this can be done in the lab. In anybody's lab it can be done with a very small setups, okay, and you get accurate results also. So, thank you very much. So, if you have any query, please feel free to write to me at kmohanty@iitg.ac.in, and I will definitely answer your queries. So, thank you very much.